Hi there. So in this video, we're going to talk about areas of triangles, which will also lead to areas of other objects. And you might feel like this is pretty straightforward, and it is. We'll use that basic formula, 1/2 base times height. But we're going to look at it a little bit deeper because there's some oversimplifications from that formula that people underestimate how to get the area of a triangle. And then we'll be able to use some trig to find namely the height that often is harder to get at. All right, so let's get started. Okay, I want to show you where this formula comes from. It's just a nice thing to see and know and connect to a lot of other formulas. And that's the thing, all area formulas come from basic ideas and notions. They don't just drop out of the sky from nowhere. Okay, and where it starts with is with a rectangle. All right, now a lot of us know this formula. I'm using different letters. We usually use length and width, but I'm going to use these letters, B for base and H for height. Now what makes a rectangle is that you have these two pairs of parallel sides, and then also you have all right angles inside of that figure. Okay, and so a lot of us know this formula, but the area of a rectangle, we usually say length times width, but now we're using B and H, so it would be base times height. So that one's pretty straightforward. All right, and so the next one we want to go to is what's called a parallelogram. Okay, and the reason I'm doing this is it shows you some nice concepts about area too. All right, and so a parallelogram has those two pairs of parallel sides, but the angles aren't necessarily right angles. All right, like that. And so we're still going to use the idea that here's the base, and then the height would be this dotted line right here. It'll be given by that dotted line right there. All right, and so what we can imagine doing now is going and cutting that parallelogram. That's supposed to be scissors right there. We're going to cut that parallelogram along that dotted line. So now if you think about it after I've cut, then I'll end up with this right triangle right here, and then I'll have this strange looking object. It's called a trapezoid. We don't need to worry about that right now. Okay, but the thing is, you got to remember what area is. Area is a measure of the space inside of that object. So how many square units fit inside that. And if you think about it, after I've cut, the area stays preserved. I still have the same amount of space inside. It's just those two objects. Okay, if I cut objects, the perimeter does change, but the area stays the same. That's a nice property to know about area. Now what I can imagine doing is taking this triangle right here and fitting it in right there into that blank space of that trapezoid. And what am I going to end up with? I'm going to end up with a rectangle. Do you see that? Okay, well, what are the dimensions of this rectangle? It has the same height as the original parallelogram because the height line is right here. All right, and then if you think about it, this length right here is the base. All right, and so same thing with the rectangle. The area of a parallelogram has the same formula. It's just base times height. All right, now let's get to a triangle. All right, so I've kind of rigged this a little bit, but here's a triangle right here, just a regular old triangle. Now, we'll still call this length right here the base, okay, and this is called an altitude. It determines the height, all right? Now, look what I can do here. I can make a copy of that triangle, all right? You see that's the exact same triangle there. And then I can flip it upside down. So that's the same triangle flipped upside down. And then I'm going to rotate. I'm also going to, so if you notice what I just did there, I did a vertical rotation of that thing, or reflection. Now I'm also going to flip it over this way. So I'm going to do a horizontal reflection. And so let's see what I can do here. So I'm just going to, you see what I just did? I just flipped it. All right, and now I'm going to move this triangle right here, and look at what shape I have. That's a parallelogram. Right here, this thing is a parallelogram, two pairs of parallel sides. So that's what makes something a parallelogram. So what I'm trying to get at here, hopefully I didn't confuse you too much with those weird reflections, But what we're seeing here, what I'm trying to get at, is a triangle is half a parallelogram. Okay, like that. And that's one way to think about what a triangle is. I know it's better defined as a closed figure with three sides, but one way, especially with the area formulas, to think of it as half a parallelogram. So what is that saying? That the area of a triangle, let me get that second triangle out now that we know if what where that formula comes from. But the area of a triangle, it's one half the area of the associated parallelogram. So that's where that formula comes from. I know that might be a little bit of overkill, but I just like people to understand where that formula comes from. Okay, now one thing about the area formula. So we know that area is one half base times height. But the key thing is what we're used to seeing from textbooks are pictures that are drawn like this, okay? And we'll see a lot of them drawn that way. I just want to point out one thing here. So it's pretty obvious right here that you would probably call this the base, and then if you could measure that altitude, that would be the height. Okay, but look in the next two pictures. There's not an obvious base, and that's the important thing about this form. One important thing about this formula is you're kind of free to pick which side is going to be the base. And the idea, if you want to use this formula, you should be able to measure the height for whatever base you used. Okay, and so part of what I'm trying to get at here, this is probably, and you know, if we were given this triangle right here, this would probably be the base, and that would probably be the height, but it doesn't have to be. Okay, I could also call this side the base, all right, and then I'm not really sure if that's a right angle or not, but the key thing is I would have to be able to measure this height, the perpendicular height from that. All right, and same thing, I could also call this side over here the base. Right here, that's looking like a right angle, so this probably is the height right there, but if it weren't, if I didn't know for sure that that's a right angle, I would need some way to measure the height right there. Okay, and so that's the thing about the formula and places where people way over underthink it. Okay, you actually have the liberty to decide which is the base, or the problem might determine that if you're given a problem. Okay, so same thing here. Let's look at this second triangle. I could call this side the base. All right, and the key thing is whatever side you call the base, you should be able to draw the altitude to get it. And so right there, that would be to get the height is what I meant to say. All right, but it could be another side too. Any side can be the base as long as you can measure the height relative to it. So there would be, I could call that side the base. Where's the height going to be then? It's going to come straight down from that opposite vertex right there. And so then that would be the height for that situation right there. And then with the third side, okay, then the altitude would come down here. So notice whatever side you call the base, the altitude is going to come down from the opposite vertex. And that'll help you with this next picture. Okay, so the key thing is, what I want to point out with this third one is, you know, it's pretty obvious here. If I called that side the base, here's then right here is the opposite vertex, and so I would want to draw the altitude coming from that. Okay, the one I wanted to make sure and point out is what if we called this side over on the left the base, and so if I called this the base, all right, right here is the opposite vertex, right here, okay, and I got to make that go straight down. All right, so to make that happen, I actually have to extend this line here, and then the height would come down, the altitude would come down outside of the triangle, and so I would need to be able to measure that height right there. I don't like that I wrote that H sideways. So that would end up being the height. Again, that might seem like a little bit of overkill, but I've just seen lots of students misinterpret that formula and think that the picture always has to be drawn this way. Now, one thing you can do is if you have a picture that's like this and it's throwing you, you can rotate, you can redraw it rotated so that this looks more like that. Now, let's think about what happens with a right triangle, since we've been talking a lot about right triangles lately. Okay, so if you remember with a right triangle, the side that's opposite the right angle is the hypotenuse. Okay, And so this side right here is the hypotenuse. And these other sides, we usually use A and B. That's fine. A lot of people call those the legs. So I'm going to call this L1 and L2. Okay, well, if I do that, if you think about it, what's a convenient side to call the base would be this side right here, and then the L1 would give you the height, right? Now, I don't advise rewriting the area formula here. We can still think base and height, but if the area is equal to 1/2 base times height, the key thing to understand is that with the right triangles, the base and the height are the two legs. Okay, the sides that aren't the hypotenuse is what I'm trying to get that there. That's a new vocabulary term for you. Okay, and the reason I'm pointing this out is just imagine having a right triangle that looks like this. Okay, you might be tempted more to think about this as the base. All right, but in order to use that area formula nicely, we want to that side right there, if you look at it, that's opposite the right angle, so that's the hypotenuse. So what I really want to get are these two sides right here, and then the area would just be 1/2 L1 L2. So sometimes what seems like the natural base is, especially with right triangles, is easier done with the two legs instead of what looks like the base in the picture. Okay, so let's look at 3 examples of finding the area with formulas that we know. Okay, so problem 1's pretty straightforward. I mostly just want to point out how to use the formula, but also units for area. But this is a very common right triangle. It's called a 3, 4, 5 triangle, and it's used a lot by carpenters and manufacturers to make sure that they have a right angle. I can explain that later if you're interested. But anyway, this is these are called a Pythagorean triple because these 3 numbers form a right triangle. Okay, but anyway, we're trying to find the area here, and so just remember, area is equal to 1/2 base times height. Okay, but what kind of triangle do we have? We have a right triangle right here. Now from this picture, it's pretty obvious too. This could be the base and this could be the height. All right, but that's a nice thing to know. With a right triangle, what you can consider the base and the height are the two non-hypotenuse legs. So now just to calculate this, then what do we have? 1/2 times 3 times 4. That's 1/2 times 12, which is 6. Okay, now be careful though, this problem has units in it, so we want to include units. Okay, remember that area is a measure of the space inside, which is the way we measure that is the number of square units that fit inside that object. Okay, and so long story short, I'm going to explain this in just a second, but long story short, area has square units, so we would say 6. It looks like we're saying inches squared. We really pronounce that square inches, and so some people like to abbreviate that instead, SQIN. Now, one thing to point out too, you can actually see what units are from the formula too. Okay, and so whenever we did that area, let's put the units inside of our calculation. So we had 1/2 times 3 inches times 4 inches, like that. All right, we can group together the numbers to get 6, just like we did in our calculation. But now the units are in there, so we have inches times inches. All right, and so that's 6 inches. And units in a calculation behave just like variables. So we have something times itself, and so that's where that square comes from. All right, so a lot of times you can look at a formula and determine what the units are. The base is in inches and the height's in inches, and they're being multiplied. So my answer should have square units in the answer. All right, and so that's another way to see, and that's a good skill to have, is to be able to look at a formula and tell what the units should be in the end. Okay, let's move on to problem 2, though. All right, and so again, this problem is a right triangle. So the way this is drawn, it looks like we should use this as the base. The problem is, and I'll just make a long story short, it'll be hard to get that height right there. Okay. The problem is, and let me show you this too. The problem is you're thinking, well, why don't I just draw an altitude right here? Then I have a right triangle. The problem is, in that right triangle, you need to have this length, we know that that entire base looking thing is 10, but we don't know how long it is over to that altitude. So we don't have a length to work with in that right triangle. Okay, and so instead, let's take advantage of what we just had pointed out to us, that in a right triangle, the two non-hypotenuse sides can be the base and the height. So let's call this one L1, this one L2. If that notation's confusing you a little bit too, you could call this A and B or X and Y as well. Okay, like that. And so now what I can do is I can find each one of those separately. All right, and so if the picture's throwing you a little bit too, make sure you realize you can redraw it this way. That hypotenuse is 10. Here's your right angle. And so here we have L1 and L2. Now I'm a little worried about space. I actually had to edit this a little bit because I was trying to crowd things in a little bit too much. So let's restart here. Okay, and so here's our triangle here. So we need to find L1 and L2. Okay, and you remember, just like in the last lecture, we got to find these separately. All right, well, let's think about how to label things on this triangle here. Here's the right angle, so 10 is the hypotenuse. Here's my given angle, and so L2 is the opposite. So right here is my hypotenuse. L2 is the opposite, and so that'll make L1 the adjacent, in whichever version of the picture you want to use. Okay, and so whenever we're finding L1, we're given the hypotenuse, and we want the adjacent. So which trig function relates hypotenuse and adjacent? Hopefully you're getting used to this. It's the cosine. Okay, cosine of what angle? 40 degrees. And see, once we start getting used to that general setup for solving, then we can shorten the process a little bit. But that's up to you. You might want to write the definition first. But what is the definition of cosine? It's adjacent, so that would be L1 over the hypotenuse. All right, and then this would be over 1. Okay, equate my cross product, so I'll get 10 cosine of 40 degrees is equal to L1 times 1, so it's L1. Now don't worry about getting the decimal for that right now. Let's just keep that in exact form. We'll go to the decimal once we calculate the answer. All right, and then for L2 then, what are we given? We're given the hypotenuse, and we want the opposite, right? All right, and so which trig function are we going to use that relates the opposite and the hypotenuse? That would be sine of 40 degrees is equal to the opposite, which is L2 over the hypotenuse. All right, so putting that all together, we get L2 is 10 sine of 40 degrees, like that. Okay, and let's just keep that as a sub answer. Don't worry about getting its decimal right now. Okay, if you just really want the decimal, then store those letters. Maybe store them as A and B. Store those numbers that you get, and so that you don't get any round off error in your answer. Okay, but now we're ready for the answer now. The area is 1/2 base times height, but those two legs, L1 and L2, are the base and the height. So I get 1/2 10 cosine of 40 degrees. Okay, like that, and then 10 sine of 40 degrees. All right, we could do a little bit more here. So make sure you realize just the numbers that are outside of the trig functions. You got 10 and 10, and they're being multiplied, so that's 100. But then I have 1/2 of that, and so what we end up with is 50 cosine of 40 degrees times the sine of 40 degrees. And then if we want to give the exact form here, the units are feet, so we'll have square feet. And now we want to go and approximate them. If you plug that in on your calculator, make sure to remember to close those parentheses around the trig functions. Remember, you don't need to type in the degrees if you're in degree mode. All right, and so hopefully you tried that, and you can see you get about 24.62 to 2 decimal places. All right, and so there's the area of this figure. We'll pick up on problem 3 on the next slide. All right, so now let's look at this picture here. Now the key thing about this thing is it's a parallelogram. Okay, like that. And so remember, I gave you the formula for it, but also think about where the triangle formula came from. That half is a reflection that triangle is half of a parallelogram. So the area of a parallelogram is just base times height. All right, so now make sure you realize here that to work with this, I could, if you don't see it already, you can think about this 8 meters and moving it down here to the bottom, right? And so we have 8 meters down here, and so that's telling me that my base is 8, all right? And so as far as the answer goes, we're halfway there. It's 8h, okay? The problem is we're not given the height in this problem, and so how can we find it? The height visually is right here, right? And so we could call that the height, but make sure you realize that's an altitude, so that's going to make a right angle. And so I can think about taking that little triangle that I have drawn there. Now, one important thing to realize, make sure you realize we don't know what this length is right here because we don't know how far over that line's going to cut. So we can't use that 8 down here in the base. But notice that that slant line is 5 meters. So I have my 40-degree angle and 5 meters right there. And we want the height, okay, like that. And so think about labeling of the sides. Here's your hypotenuse. So the 5 is the hypotenuse, okay. And then here's my given angle, and h is opposite. So h is the opposite side. So we're given the hypotenuse and we want the opposite side. Which trig function should we use? We should use the sine, okay? And so what would that say? It would say the sine of the angle, which is 40 degrees, is equal to the opposite, which is h, over the hypotenuse, which is 5, like that. Go and equate your cross products. We're going to get 5 times the sine of 40 degrees is equal to h. All right, and so now we're there. Okay, and so we get the area is equal to 8 times h, but we just found that h is 5 sine of 40 degrees. Like that. 8 times 5 is 40. That's interesting. We have these two 40s. Okay, like that. And so there's my area in exact form. So now I just want to type that in on my calculator. 40 sine 40, like that. And I get 25.71 approximately. And then don't forget your units. Our original units were in meters, so these would be square meters or meters squared if you write it that way. All right, so let's look at how we could find the area of a regular polygon. So if you remember in the last video, we talked about what regular polygons are. So regular means all sides and angles are equal. All right, and so this is the same pentagon that we looked at in the last video. We have a pentagon, a regular pentagon, and the distance from the center out to a vertex is 8 centimeters. All right, so how this all ties in here is this is very similar to what we in the last video. We found the perimeter. Now we can find the area, and it's the same thing. We can divide this into 5 congruent triangles, being a pentagon, okay, like that. And so what's significant about that, the area is going to be 5 times one of those triangles areas, okay. So all we got to do is find the area of one of these triangles. All right, I'm going to come down to this one in the bottom here just to so things might be a little easier to look at. Okay, so that's the one I'm looking at, is all I'm trying to get at here. All right, so the key thing is, remember, the same process. This makes a full circle, so that's 360 degrees. So then how big would this angle right here be? That angle right there is going to be 360 divided by 5. And so let's call that theta for now. Oops, I've got to switch back to my pen. Let's call that theta for now. Okay, and so theta is equal to 360 degrees divided by 5, which was 72 if you remember. Okay, so now I have this triangle here. Like that. This angle, I didn't draw that angle very well, did I? That's going to bug me. All right, let's try to draw it looking more like the triangle in the picture. All right, so that's 72 degrees. Key thing is this side is 8 and this side is 8 centimeters. All right, but we need the base and the height, okay? And so, now one important thing to realize here, this is not a right triangle. There's no right angles in here. We could figure out these other two angles, if you think about it, there's 180 degrees in the whole triangle, all right, but we've just used up 72 of them, and so that's going to be 108 that's left, but I got to split that equally between those two angles. Those would be 54 degrees, won't they? I'm doing all that in my head. Let's make sure that that's correct before I carry on. 54 times 2 plus 72 is 180. Okay, so anyway, so we have this set up, but we don't have any right angles yet, okay? But what can I do? I can take advantage that this triangle right here is isosceles. These two sides are equal. That means if I drop an altitude right here, it's going to bisect that angle. Or I could take advantage that I have a 54-degree angle. Okay, so I'm going to drop that altitude. And basically what that does, that cuts that triangle in half, okay? And so I end up with this picture right here over on the left, all right? And so I have 54 degrees here, and then I know this side is H, okay? So now be careful. This can be the base and this will be the height, okay? But we're trying to get the area of this entire triangle right here, and we've just cut it in half. So we're going to have to be a little bit careful once we use the area formula, all right? And so, but anyway, I'm going to skip, this video is starting to get a little long, but no, I'm not going to skip anything. Okay, so label your sides, all right? There's your hypotenuse. All right, if I'm going to use that 54-degree angle, there's the height is the opposite angle, the opposite side, sorry about that. And so B will be the adjacent, all right, like that. And so then we need to find those two separately. And so then for H, to find H, we're given the hypotenuse, and we want the opposite. Which trig function are we going to use? We're going to use sine of 54 degrees is equal to H over 8. All right, and so hopefully you're starting to see this process a little bit more. When I equate my cross products, I'm going to get 8 sine 54 degrees is equal to H. So we have the height, all right? And then for the base, B, okay, like that. So for the base B, then we're going to have, we're trying to find the adjacent side, so we're going to have the cosine 54 degrees is equal to B over 8. Go and create your, we're finding B. I didn't mean to write an equal sign there. I'm starting to rush and I'm being a little sloppy, aren't I? Okay, and so we write this thing over 1. We equate our cross products. We get 8 cosine of 54 degrees is equal to the base. All right, now here's where we got to be careful. All right, what this is saying is that the area of this triangle is 1/2 base times height. So the base is 8 cosine of 54 degrees. And then the height is 8 sine of 54 degrees. Okay, group together your numbers that are outside of the trig functions. That's 8 times 8 is 64. 8 times 8 is 64, but divided by 2 is 32. So I get 32 cosine of 54 degrees, sine of 54 degrees. Okay, so now, but see, that's the area of that right triangle, okay? But what are we really trying to get? We're trying to get the area of this entire triangle right here. This entire triangle is composed of 2 of those right triangles, okay? So the area of this thing, the bigger triangle, the area of this is twice this right here, okay? Does that make sense? Hopefully it does. Now, the one other thing you could do too is if you just want to use this right triangle right here, just ask yourself how many of these right triangles are in this original picture, okay? Like that. But now, so what do we have now? This expression right here that we have, so it's 2 times, and let me go ahead and write it. Again, I'm being a little bit sloppy. So that's going to be 2 times 32, so we get back to that 64. Cosine of 54 degrees, sine of 54 degrees. Okay, so that is the area of one of these triangles right here, back in our, getting back to the problem. Okay, but we want the area of the entire pentagon. How many of these blue triangles are in the pentagon? There's 5 of them. We mentioned that up here too. Okay, and so we're ready to get there. The pentagon area is equal to 5 times 64 cosine 54 degrees, sine of 54 degrees. So we do 5 times 64, which is 320. So I'm just going to save myself a little bit of space here, and so we get 320 cosine of 54 sine of 54. And so now that's the exact answer right there. So now we're just plugging it in on our calculator to get the approximation. And so we get 1 to 2 places. That would be 152.17. And then our units were centimeters. This is area, so it's going to have square units. Okay, so that's the area of that pentagon. All right, so I hope that makes a little bit of sense. I know some parts get a little confusing, but you just take it a step at a time. One important thing too is whenever you're doing these kind of problems, especially with me, I won't ever give you problems that you haven't at least seen the tools. You might have to do some creative thinking to use those tools, but I'll never ask you to find things that we don't have the tools for. Why? The reason I'm pointing that out is whenever you see problems like this last problem, don't look up formulas on the internet and just plug into those formulas. You're not getting anywhere with that. You're not learning anything. And what we're trying to learn is some techniques that'll help us solve more sophisticated types of problems. All right, I hope that helps, and I wish you the best.